thank you the team from EcoSource, especially Jason, Cornelia, and Moroka, who are nicely organizing this event. And for me, it's a pleasure to be here and exchange some new information about what is in FEFLOW. I would also like to give you perspectives of where are we going in the next months. And obviously, I'm very happy to take any questions about the release or about FIFLO in general, if you have. For those who doesn't know me, my name is Carlos Rivera Villarreyes. I work at DHI since almost 12 years. I'm based in Berlin, Germany. I'm responsible for the product FIFLO globally in terms of the business development, but also in terms of the technical, the technical direction where the software goes with every release. The agenda today, from my side, I will have one mega announcement to do. Then we will have some recap about FIFLO 10. I think it's worth it to mention a few things which were developed in the previous version and that you can connect what is done now with FIFLO 11, the follow-up. We will have a live demonstration and a Q&A session about all these presentations. For those who already participated in the first release webinar organized a few weeks ago, some of the slides will be similar, but the difference today that I have more time to elaborate the live demonstration and obviously to take more questions from you. So the main announcement that I would like to do today is invite you to the FIFLO International User Conference. We are having again, after 2 years, the conference this time will be in Canada, in Montreal. It's a nice location. This will take place between the 29th of September to the 2nd of October. We have opened a call for abstracts last week's. If you are would like to participate in the event, share your ideas, knowledge, and interact with other FIFLO and groundwater modelers around the world. So I welcome you to, or invite you to go to the website, explore what is in the agenda. We will have a lot of nice special training workshops, and the community is really looking forward to this event. After the success that we have in Hamburg, Germany, the last time, some of you from South Africa participate. So I hope to see you also again in Canada later this year. Okay, so let me start doing a short recap about FIFLO 10. So the version before what we are discussing today. FIFLO 10 was a major release for the software because we target different aspects from meshing, geological modeling, numerics, visualization, usability, and of course the FIFLO and programming interface. So I'm pretty sure some of you already know this, but let me elaborate some of these concepts so that I can follow up later in the FIFLO 11 presentation. So in the FIFLO 10, it was the first version where we introduced our geological modeling package. We will call it implicit modeling of geological surveys. So from the 3D super mesh, we elaborate a new workflow to import borehole data, and this borehole data is used to build geological surfaces. At the same time, we see that most of our users are really building and trying to build complex numerical models, so 3D models with complex geological information, maybe different faults, inclined boreholes, etc. So we introduce more flexibility in the way how we create meshes. At the same time, it was the time to modify the way how FIFLO calculates the transport equation. When I say the transport equation, I'm basically talking about the mass transport and also the heat transport equation. If you have been working in projects of water quality or geothermal, you will know that we have two main definitions for the transport equation. So one is called the convective form and the other is the Berger form. This exists since almost the beginning of the software, so the late 70s. And they were nice for different cases, but sometimes we reach the limits. So we introduced a new formulation that we call a standard transport formulation, which has the best of these two existing formulations. It's easy to use in terms of boundary conditions, and it has a very clear definition what the boundary is. So if you expect to set some grams per day, for example, in your injection boreholes or in ponds, so you will actually get exactly that through the rate budget balances. For users working in deep geothermal or in systems where temperature plays a role, this could be also an interesting case in underground mining. So we extend what we call equation of states. Equation of states basically say how the fluid is described in FEFLOW. And the fluid primary in our system is water. And this fluid depends or has a density and has a viscosity. So we start working now with a full definition how we modify the density. So density now can be changed by, it was possible to change, but now it's a bit more easy to use. We have a full density function depending on concentration, temperature, and pressure. So the pressure component is basically new. And this is nice for people working in deep reservoirs, either geothermal or maybe users working in seawater intrusions, or maybe there are users working in lithium environments, which is nowadays quite interesting in mining applications. So in those cases where you have upper salines system or environments where there is an important um, relevance in modeling the density, you will get benefits of this equation of states. Then FIFLO 10 use a lot new technology for visualization. So we implement online maps, visualization, quite nice and practical. You define your projection and then FIFLO can display immediately the location of the mine. If I remember correctly, actually, this is a location somewhere in Congo. We have the possibility to split the way how we record in the budgets in the charts. This is also nice because in the past we only get one single component. In this example, we have one single line, which is the net. But sometimes you would like to see the positive to the and the negative components, so the inflow or the outflow. And this is also really practical. And we have a new visualization what we call isosurfaces used as canvas. So you can plot, for example, the location of the water table. That is exactly this case. So this is a pit. So we have here the drawdown of the water table, and I can plot exactly on the location of the water table anything that I want. The conductivity, in this case, I'm plotting pressure or hydraulic head, but I can plot also concentration, temperature, or anything. And we obviously extend our Python interface with new APIs. So this was released in November 2024. Now we come to the version today, which is FIFLOW 11. FIFLOW 11 was released this January, late January 2026. And it's again a major software release. It has multiple significant changes in the software. We keep working in our geological model, and this time we have a full implementation of the geological model. Obviously, there's still few things to be done, but it's very robust in this version 11. We have more workflows about meshes. We extend the way how we manipulate our wells through the well manager, how we group them. Especially, we are also targeting a lot of different features for geothermal market, and FIFLOW 11 is a version faster than ever. So we have introduced a significant performance boost on the way how we compute the different calculations, and I will elaborate this in the next slices. So if you want to get more details about all these features that I will explain today, everything is explained in our online help. There is always a what's new page where you can see all these different changes. So let me start with the geomodeling part. So we introduce a new concept, what is called now in FIFLOW 11, a structural model editor. And this is the foundation and the base of all our different workflows today. And it will be the future tool for developing geomodeling tools or geomodeling workflows in FIFLOW in the next consecutive versions, in FIFLOW 12, 13, and so on. So I will also emphasize through my slides what features you will actually access. Some of these features are introduced with the concept of FIFLOW advanced features, which are SMA benefits. SMA stands for Software Maintenance Agreement. So for those customers who has access to SMA, they will get some of these features. So I will explain later in detail which are the ones. Sometimes you will read it in my slices. And obviously for specific subscriptions, we are also giving access to these tools. So this is the structural model editor, and the structural model editor give you a full overview about the boundaries. So what is the extension, what you would like to model, faults, so you can import surfaces or define surfaces that you create in FEFLOW as a fault. You can have one or multiple ones. A stratigraphic page where you define your stratigraphic pile, the definition of the different materials and the interface between the materials, and the raw information, the boreholes. So what do we support today? And this implementation is actually, as we are speaking, extended, and we have a lot of developments now in the next months. So by the FIFLO conference in September, we will reveal most of the expansion of this structural model editor. So as I mentioned before, the structural model editor is defined by these four different pages. Um, but let's look what we can do in terms of geology. So we have a stratigraphic pile. This pile can be built automatically if you import a number of boreholes where with some rules we detect certain logic of the boreholes. The logic depends on the material. So if you have some let's say common definition of materials in your different boreholes, we will identify this, build a pile. The pile consists on units. So I have here 7 units. I have interfaces. We have today support 3 types of interfaces: deposits, erosions, and base slabs. We will implement in the next months. Actually is a done, but we didn't have time to incorporate in the graphical interface. So the mathematical part or the background part is completed. We will have an interface that we call unconformal and conformal. For example, if you would like to simulate um, diapiers, so that type of geometry will be implemented in the next months, or will be available in the next months. So these interfaces can have a type. The interfaces are defined by a set of points. These points can come automatically from the borehole. So when we detect the boreholes, we detect the materials, and we detect the interface between materials, and we extract, for example, or we draw a point in the interface between consecutive materials. And these are called horizon points. Horizon because it defines the horizon, and points because it's a set of point data. For the future, also happening now, as we speak, we will implement the possibility to define surfaces. So you can bring a geological surface coming from GoCAD or Leapfrog, and we can take this surface and use it as additional constraint for our calculation, or polylines as well. Then, so obviously, what is quite nice to have in this interface is that you can quickly play around with the type of interfaces. So what's going to happen if I change this interface tree as a deposit? So this is a play model. So don't look at much into the details. It's just for demonstration. So I can change easily what is the interface. It's either a deposit or it's erosion, and then it will obviously influence the calculation of the geology. So you might be wondering at this point, so why do I really need to have a geological tool in FIFLOW? And the answer is very simple. So obviously you can do all these things and even more complex things, if we are honest, in different softwares. That's granted. What we guarantee with the FIFLOW built-in workflow is that the geometry that you build with our toolkit is a measurable geometry. So we will build geological interfaces and units which can be measured later easily in FIFLOW. That's the whole motivation. Because we have a lot of tools still to, for example, to import external geological data sets. You can import these data sets, but we have been learning from the last 5 years is all these data sets comes with a lot of data that is not ready to be measured, because these other third-party softwares are very good for the geology, but they have been not designed for numerical calculations in finite elements. So as soon as you start building your complex geometry based on external data set, we will identify problems. We have tools to repair these problems, but obviously there is a limit that our tools can repair or correct. Going more in the direction of meshing. So these tools that I was mentioning before are called geometric tools. They are used for correct different type of data. So I will explain you in a minute how we correct this. And when you have, we call it a boundary representation. So it's a super mesh project that is ready to be meshed. So you can take it. You can use the standard mesh generators for the 3D super mesh. Standard means tetrahedral mesh generators. We introduced a new option now called layer mesh generator. So you can build your layer mesh from the 3D world directly, which is very nice because sometimes you lose the flexibility if you go for a tetrahedral mesh. So here you will have a typical prismatic mesh in FEFLOW, and if you have pinch outs, we can preserve these pinch outs with a layer continuity by setting a minimum thickness. Then the layer configurator has been now modified strongly. So this layer configurator exists in FEFLOW since probably 20 years more. So now we are introducing new concepts. We have revamped the whole this design of the configurator that is more simple to build meshes. So we want to actually help you to simplify models, to create models that are complex, but at the same time, the mesh discretization is simple enough, which is also has as a positive consequence speed up the calculation. Let's look about these different geometric tools and layer meshes. So for the geometric tools, we have a toolbar. It's called Super Mesh Processing. In the panel, we have a toolbar. It's called Geometric Tools. And these tools, they have different purposes. So just let me explain. So if you see here, I have a fold, which is very fine discretized, and there is a small layer or a box. So this is not meshable. If you throw it to the mesh generator, it will give you an error message because this is not fitting. So we have one tool to compute the geometrical intersection. It will basically intersect every single triangle that you see here with the triangle of the top of the face and the bottom of the box. We have the intersection computed, then we can remove what we don't need, so everything outside, and we can also retriangulate the surfaces so that the quality of the mesh is nicer. This is an optional step because when we build a tetrahedral mesh, we do this step anyway. So you can use these tools to correct different data sets. These data sets can come from shed files. If you work with shed files, must be in 3D. CAD data sets, so DXF, DWG, leak files, so like LFM, and GoCAD files, TS, ML files. So once you have a super mesh that is ready to be meshed, like this one, so this was built by using the geomodeling package in FEFLOW. So I have some material information about the unit. So still this is super mesh, so there is no tetrahedral or prismatic elements in the inside of these different units. So we have a new option called layer GOD layer, which it just requires one parameter, is a minimum thickness. So this is required for cases where there is a pinch out, for example here. So this layer is basically coinciding with the base of the domain is disappearing. So to continue the layer, we set this value, I would say here in this case 1 meter, and it will have the continuity all the way. This configuration, they do not necessarily need to happen at the bottom, at the top of the model. They can happen every location of the model domain. So how do we do this? So there is a algorithm obviously behind the scenes that it needs to be basically checked whether we can build these meshes with this approach. So we require a 3D super mesh project. We require a valid structural model. So this is the model that I was mentioning in the structural model editor, and it requires what we call a no multi-set configuration. What is a multi-set configuration? If you have a vertical plane, obviously you cannot have a vertical FEFLOW slice that is going all the way from the base to the bottom. So in this case, it's not possible to use the generator. So what you will need to use is the either GeoD structure or the gen. Okay, so you have now a mesh that is potentially made from prismatic elements, or you have existing FEFLOW model. What can you do now? So we have enhanced the way how we present all these different workflows in the layer configurator, and now then actually it's different. It's called different. We have a slice layer configurator, and I'm going to explain why introduce this new terminology. So we have now three alternatives how to resolve these geological pinch outs. The existing one and the very classical approach is what we call the minimum slice separation. Slice separation is because if you have a pinch out of the layer, a layer is defined by two consecutive slices. So we set the height of the slice, and this minimum height avoid basically the pinch out of the layer. This is called a slice structural mesh slice, because the slice has to still run all the way from the beginning to the end of the extension of the model domain. So this slice will go all the way like this and all the way like this, and here we will have a minimum thickness. Then we have a new approach, what we call a structural pinching. It's called layer structural pinching. So here we introduce a new concept that so far a layer in FEFLOW was always extended all the way laterally. Today we have our layer in FEFLOW 11. A layer could be this part or could be this part. So we can have one layer being discontinuous, or two different layers in case I have a displacement of one unit here. So this is a new approach, and I'm going to elaborate this approach in my different slices. And then we have the unstructural pinching, which basically is we will build a tetrahedral mesh if we have cases of intersection or coalition between the different slices or surfaces. So this new layer, this new concept of layer structural pinching is quite practical, because even that your layer does not extend the whole extension of the horizontal domain, it will be treated as a layer in FEFLOW. So you can go through the special entities. You can look the layer that you want. In this case, I'm looking the layer 25. There is this one. If I have I will have access to the slice view, so I can look the top and the bottom of layer 25. Even there is a small area, and assign properties, assign boundary conditions. We have also activate or enhance our different tools for selections to operate in situations where the layers are discontinuous. So if you can copy, if you have a boundary on the top, you can copy the boundary down. So everything that you normally do with layer based models, layer, or we call it now slice structural models, is supported with this new approach. How does it work? So you have the layer configurator again. So layer is 3D slice layer configurator, to be precise. The workflow on the left side is exactly the same. So you put your slices. Every slice has elevation, either constant or is interpolated by a set of points. Then we will detect, or we could detect, whether there is a violation of these minimum vertical separation requirements. So you can test the value. So I know that I build my models with a 0.1 meter minimum thickness. So I can ask them to evaluate this, so I can resolve this. And when I resolve, it comes with three potential options. The enforced minimum slice separation. This will be standard FEFLOW models where the slices will run all the way through the complete lateral extension of the domain. Structural pinching, it will do a geological pinching in an organized manner by preserving the visualization in the slice views. And structural pinching, this could be a tetrahedral mesh or partially tetrahedral mesh. So let me try to demonstrate this in examples. So I have an existing model. The model is quite large. You see here it has about 4.7 million nodes. It's a significantly large model, so it takes some time to run. I have a lot of complex geologies. So there's a fault here. And because we are using this preservation of this license in previous software versions, so all my slices needs to run all the way from here until the end. So you see I am accumulating a high number of slices here. So this is important to know, because these are tiny elements, but still they sum up to the matrix. So we are escalating the size of the matrix significantly, which it will obviously produce a decrease in the performance. So calling this new approach, what I can do is I basically, if you look here, I can simplify the number of elements. Simplifying the number of elements or nodes, actually, it will simplify the number of equations to solve, and the model per se will run faster. So we can evaluate this in a cross-sectional view. It's probably easy to see. This is the original cross-section with all these tons of different slices. So I am from 4.7 million nodes, and the reduction is a factor of 4, about 1.4. So you can basically more or less say that your FEFLOW model will run 4 times faster with this new setup. Nice also is if you have existing models, you can use this approach already. So if you have parameterized the model, you have calibrated already the model, so you will have all this information here. This is, in my case, the conductivity. I can take this, I can open the 3D layer configurator and then evaluate certain limit for the pinching and eliminate all the layers with slices that I do not require. And it will it will preserve the assignment of the material properties and boundary conditions. We also have it interactive, which is new and very, very, very nice. So if you, for example, see that you would like to, I don't know, whatever, pinch out this one small here, so you can create a selection of elements or nodes and then use the new tool called fuse delete, and will basically collapse the elements heights, and it will eliminate this additional set of nodes. You can do the opposite if you have already created a layer with the structural pinching, and now you will need to add more slices vertically. This was impossible in previous software versions. So because we block this workflow as soon as you move from or you change the topology. So now you can take a selection of elements and include different layers. It's called split layer tool. Changing the topic now, we will be discussing about the well manager. The well manager has been also restructured in a more intuitive manner. So we disconnect the part of well creation with the existence of the wells. So before you need to have wells created, and then you group the wells. So now we can have groups that are empty. So you can create a number of groups, as many as you want. Each of these groups could have one or multiple rules or properties, depending on the case. We offer rules for geothermal applications like the open loop, or we have rules for only all type of problem classes like activation, sharp properties, and distributed flow rate. So you can create all these groups. We can import, export all this, nice, and then you can later assign these groups to the wells. And why do we need this step is because now we do it also interactively. So in the well manager, what is really powerful, it can help you to do a lot of operations with wells. But as soon as you have many wells, so it might be a bit uh, not so easy because it's a tabular view. It's a tabular view. And so we introduce a new option in the editor toolbar, which allow you to assign well groups to a different set of wells. So how do you call this option? The option is available for well VCs, for multi-layer wells, and borehole heat exchangers. So meaning the 3 types of wells that we support in FEFLOW. So you normally will go to the toolbar and assign, for example, for the well VC 20 liters per second as a pump rate. Instead of assigning, you can click on the icon and it will change to the well group assignment. Then you can take any of the existing selection tools in FEFLOW and simply take from the list, from the combo box, the group. It could be existing, a group already with wells, or could be a group which is empty, and then you just assign it. This is really nice because you can also display the names of the well groups. So if you have many groups and many wells, so you can know really exactly what you are doing within the different assignments, which is really, really practical. So Geothermal features. So I think maybe you are not doing much of these geothermal features, but I think it's probably also interesting to see where is all are operating with the software. So we introduce a new type, what we call open loops. So open loop basically is you have a doublet of injection and a production well, where you either you pump, then you put the water back. The water come either with higher temperature or a cold temperature. So you describe this relationship by a difference, by a delta T, or by a power demand. So we have a special editor dedicated to create this type of systems. It's really nice. And also we introduce new type of charts for geothermal applications. So everyone who is working with geothermal, we can have a number of, you can evaluate easily your results. And these are the type of charts that we present for this open loop system. These are totally new charts we didn't have. So we can look temperature um, difference. We can look the temperature at each of the boreholes. Then the flow rate obviously is interesting to know. And for the case of also closed loop systems, an open loop system, we can nicely monitor the rate. So the heat rate, which is the power, which is basically important for the designer who would like to know how many kilowatts I can extract from the reservoir. Beside this specific improvement, we have general improvements as well. We have enhanced visualization of the cross-section views. Some A tool which was asked many times, so we decided to prioritize it, and is the possibility to visualize in FEFLOW cross-sectional views observation points and boreholes, or actually multi-layer wells, and any type of boundary condition. So you can plot here your river on top. You can put the different well VCs, boundary condition for the mass transport, the multi-layer wells. How it works, we have a thickness. Every cross-section has a virtual thickness, and if the information is inside or covered by this thickness, we will display it. And the thickness is adjustable, is user defined. You can modify this thickness and then see how much information you would like to plot or not to plot. Next is we have Python scripting capabilities now has been redesigned in FEFLOW. So we could have done a lot of things already in Python. From outside is obviously still the case. So you can open your PyCharm, Anaconda, Conda, or Miniconda, or the interpreter that you like. Connect your FEFLOW programming interface with this interpreter and run the FEFLOW library from outside. From inside FEFLOW, we have some possibilities, but it was very limited. So we are in this version of the software FEFLOW 11, we're extending the Python scripting capabilities in the graphical interface. That's the message. So what you can do today is install packages from FEFLOW, provide a formatting. So you can we have a default formatting about keywords in Python, for example, the for, the in, the print. You can, or you decide your own formatting as well. We have now what we call Python scripting views. This is like another type of view. Today we have 3D supermesh, a slice view, and 3D views. Now we will have a FEFLOW, a Python scripting view. You can open many of these views, so which is very practical because I can have pieces or snippets of my script in the multiple views, and I can execute it independently if I want. These scripts are saved in FEFLOW in the FEM document. These scripts can be also today encrypted. This was also required by many consulting companies who operate with these scripts and FEFLOW, and sometimes they need to deliver the FEFLOW files to authorities, and obviously they would like to keep the intellectual property of the Python script, so they can encrypt the Python script so that it still runs in the FEFLOW file, but the end user will not see the content of the scripts unless this person has the password, obviously. And we have a new, what we call Python scripting panel, which is a Python console. Which we initialize automatically that Python in the terminal or in the console. You can write your commands, you can bookkeep your commands, etc. So it's really, really practical. And this is the full extension of the scripting menu. We have the edit script, execute Python commands, run, go to line, find, replace, etc. And under settings, you will find the installation of the packages, but also the formatting. Okay, so we extend also our APIs to support access to different geomodeling tools and also Python extensions. So we have a new package that we call FEFLOW Advanced Feature Python and Geomodeling. So the geomodeling part is give you access to all the structural model that I show you through the graphical interface. You also have access through the Python interface, for example, for the creation of 3D supermesh. Now in Python, we provide new ways to, a way to interpolate. This was not possible before. So now we use the FEFLOW interpolation routines in Python to set parameters. You can nicely parameterize conductivity or any value of elevation, for example, to build your models. You have access to the geometric tools to repair external 3D datasets, access to the mesh generator, so you can call the layer mesh generator and structure mesh generator, etc. in 2D and 3D. And we also have here, we have changed all the way how we implement the fracture elements in FEFLOW. In Python, these are really straightforward to use now. FEFLOW computes faster than ever. That is the message that we are going out and send it. We have changed the way how we compute the different things. So the physics is the same. Basically, we have rewrite the methods in a more efficient and smarter manner, if I can say it in simple words. So it's to expected that through different applications, you will see an increase in the performance. This increase in the performance obviously depends between case to case and type of application or problem class that you have. To give you some examples, I brought here a few things. So this is, for example, a layer-based model with quite large, so 1.2 million elements, and reducing PADISO. So in FEFLOW 10, it was 26 minutes. In FEFLOW 11, it's 10 minutes. So it's still it's a decent speed up factor for a phreatic model, and this is a very good one. So it's the model is still not that large, but especially for models with second and third kind of boundary conditions, there was a significant way how we call the matrix how we assemble the matrix. So we basically we modify this, and what it used to count 1 hour now is 27 minutes, which is quite good. And so also for a geothermal model, so we have customers working with a lot of borehole heat exchangers. Like this specific case was 435, which is a lot. It takes 23. Now we are 9 minutes, 59, 10 minutes for this deep geothermal model. This is one way. So you can, if you start running your models in FEFLOW 11, you should see some performance. Again, depends a bit on the problem class and the configuration. There are some configurations that are more strongly impact, but in general, you should see something. The other option how you can speed up your calculations is we introduce a new option called iteration control maximum cycles of boundary conditions constraint per time step. So constraints are ways how we manipulate boundary conditions. So we decide whether the boundary is on and off, or whether we need to swap from one boundary 1 to boundary type 2. And to do this, if you are have a transient model, we need to check in every time step. Internally, we have a number of iterations. The default is 30, which is quite a lot. We sometimes see that between 5 and 6 could be enough. So you can go here and modify this. You can minimize it, for example, 3 or 4. And then if in the time step did not agree to a final configuration of the boundaries because the 3 or 4 cycles for the constraints were not enough, then FEFLOW will move forward to the next time step, but it will keep the configuration that it was found in the last iteration, let's say in the iteration 4 of the previous time step. So this is something that you need to test, and depends a lot in your configuration. So in models where you have constraints, like in seepage phase models, what you are using for the watering application, so you have a head constrained by a flow, or sometimes you have well boundaries constrained by a minimum hydraulic head, or in reverse. So you can just try this configuration, reduce the number to, I would recommend you a 5 or 4 or 5, and then try to learn how you can speed up more your models with this control. Licensing, so I just have one slide. I think Jason would like to talk a bit more of licensing, but mainly from the FIFLO part. So what do we have? We have, so as you have been hearing, we have a new license manager. It's called the DHI License Manager 2026. This is the first license management that is not developed entirely by DHI. So we use a third-party software called software called Revenera, and this is a very famous licensing tool used in many large applications. If you are working with software, Autodesk, Bentley, etc. So these guys are also using the same backbone technology. So we use this license tool to basically bring you more security, hopefully easy workflows, especially if you work with different software DHI products. So you can do all this directly from outside FEFLOW. If you have installed FEFLOW 11, we have a mini tool called FEFLOW License Overview where you can import your file and then you are up to ready to start running with the simulations. It gives you a nice overview about your aspirations, about aspiration also for the advanced features. And we have been onboarding the different groups of customers step by step. So you might have already received an email about this onboarding process, which will explain you. So if you have any questions, so obviously the HI customer care is looking forward to help you with that. Okay, so I start my presentation telling you we have a number of features which are dedicated to certain modules. And this is the concept of the FIFLOW advanced feature. It's not something new. We start with this concept already, if I remember correctly, 2 or 3 years ago. So now we are basically expanding this concept with 3 different modules: geomodeling, geothermal, and Python. The simple to explain is if you have, for example, obviously, if you have a geothermal subscription and or you have a FIFLOW FH3 professional with maintenance, you will get these additional tools for geothermal FIFLOW Advanced. Geomodeling and Python, these are softwares, these are special capabilities offered for mining subscriptions, groundwater subscriptions, and for those who are using the Flow subscription, that is the low entry level for accessing FIFLOW, they don't get these features, but we have recently introduced a new subscription type called Flow Advance, which is a FIFLOW F3 license. F3 will give you access to the full capabilities for flow in 2D and 3D. And on top of that, you will get access to FIFLOW Advanced, the geomodeling part, meaning all the geomodeling tools for building your own geological model in FIFLOW or using third-party geological software, and the advanced methods that we develop in Python, meaning the regionalization methods and access to the geomodeling tools via Python. So we will start in the next weeks a campaign to upgrade customers with a very interesting price. And I would like now to jump to the live demonstration. So if you already have some questions, you can please start typing these questions in the chat, so I can read it after the live demonstration and take it. Or as Jason was saying, we are obviously more than happy to, if you can speed your questions or activate your camera. But let's do this after the live demonstration. So this is FIFLOW 11, and so the layout didn't change much. So I'm gonna open first a file which is I have already prepared for the live demonstration, so that we don't lose too much time in setting up the whole. So I'm gonna open this one here, and we will start with the geomodeling package. So this is my super mesh. In the super mesh, I will put back the faces. I only have a cube. So I have only the outer faces and nothing inside. Inside, except we have the boreholes. They have some logics. The boreholes can be imported or built inside FIFLOW. So I'm gonna open the structural model editor, and you can open it from here, structural model editor, or you can press F8 And we have the editor here. The editor is empty except the part of the boundary. So I save some time and have defined this boundary. So the boundaries are basically a list of different surfaces. So I have my box, and my box has been split in top, bottom, or top, base, and size. In the side, for example, I have different pieces. So this is a requirement. So you need to define the boundaries because we need to know what is the extension that you would like to model, right? So false, I don't have for false, but if I would have a fold, I can basically click on the plus and create a new fold definition is called, and create and choose the surface which define the folds. Let me remove this one. And when you have the folds imported, if that's the case, we have a tool which is basically building these different fold blocks. Fold blocks are this part of the domain. So we have the cube, and the cube can be, if you have a fold in the middle, it's cut maybe in two pieces. So we will have two blocks because our calculation of the geological model will take each block and then run the geology inside of the block. Stratigraphy, no, I don't have changes. There is nothing. So I'm going to demonstrate how to create this. And boreholes, we have all the different boreholes. So the boreholes are selected as soon as you click. So you can import boreholes. So it requires a text file, or we have our own file format, which is also ASCII based. So you can easily create these files, and it's basically a list of coordinates and material, nothing really fancy. Okay, so the first step is I would like to extract the points between consecutive units. These are called horizon points. And it will tell me, okay, the stratigraphy is empty. Yes. Should I should create initial stratigraphy? I will say okay or yes. And the stratigraphy is built based on the materials. So we have a block of material. These materials are still empty. So there are no blocks because we didn't calculate anything. One unit could be one block, or one unit could be different blocks. If we have faults, the unit will be cut in pieces. Interface, the interface is created by a set of points, and I have automatically extract the points from the boreholes. Additionally, I can click on the plus and I can load another file, or I can select another list of points and add it as additional constraints for the geological modeling. These points, they have a weight, which means I could impose which part of my data has more relevance at the moment of building the geology. And the idea behind is we are preparing all these tools today that in the next months we can reveal a full uncertainty be propagated on the geological model. You can, for example, imagine that if you have data sets where maybe you have few points, maybe there is a borehole which was measured, which was drilled, I don't know, 30 years ago, was not very well documented. So you can put a low weight. The new information or data where you have more, or locations where you have more data, you can increase the height, the weight, basically. And with this way, you can manipulate and force how we can build the geological model. Other parameter is the average thickness. This parameter is computed automatically, average based on the geology. You can also say enforce if I have my chart layer here that I know that is 500 meter approx, because my geological interpretation or somebody is telling me this, so I can provide this input as a constraint. Remember, all what we are doing here is optimization. So we set a number of points. We are building behind the scenes a mesh, a triangular mesh, no, sorry, a volumetric mesh. And we will build all these surfaces on the fly and then build the geometry piece by piece. So if you, for example, have a set of points which are coming from the boreholes, and then you provide a thickness that is no sense or contradicts a lot to the points, it could be that is basically the optimization does not come to a point. But this is also something obvious. These interfaces, they have points, as I mentioned. They also have a type. You can change the type here. And when you are ready, you can press generate implicit surfaces. Implicit surfaces is because behind the scenes we are using implicit modeling of geological surfaces. We are not doing interpolation like done in other softwares. It's not interpolation. We are computing the surfaces that is passing through all the different points and following and respecting all the different constraints. Constraints are the faults. So if you have a fault somewhere in the middle, it obviously will perturb the ISO surfaces that we are building. If you have different types of interfaces, it will also perturb this calculation. So for this model, it will probably take about a minute. Um, it's relatively quick, and this is also something that we are improving in every version. So we like to boost also the performance of this technology in the next release. So this is what we call a structural model editor. Today, through Python, you can build a lot of information. We are setting up today in Python methods for accessing this stratigraphic pile. This is not ready, but this is something that we will publish in the next update, I will say, which is coming beginning of June, if I remember correctly. So now we have it. So I can leave this, and if I go here, I have built a geology in the super mesh. This is a super mesh. We only have the surfaces. We do not have yet the volumes inside. So I can go back and now inspect. This unit is consisting in a block. I have a block here. The tool has been designed that you can interact with the different parts of FEFLOW. I can look the interface. This is the interface here. Let me deactivate the edges. I can see the clean interface. You can check the interface is passing or not the contact points. Then we have the next block and so on. So you can use all these different options to review your structural model. This information here is now available in the meshing panel in terms of blocks. So it's ready to be meshed. Inside the blocks, you have the different surfaces. So for example, contain parts of the box. Remember, box 0 was the top, but the interface 1 is the contact between the two different units, 1 and 2. So we are now ready to create a final element mesh. If we go to GeoD layer, so I will show you one of the mesh generators, the new one in building layer-based models. Generates, and it's gonna use the generator to build a numerical mesh for FEFLOW. So here we have the mesh. We have this slice view. I will close it for a moment. I will also go here, and now we can see that if I plot the material regions, the model comes already with information. So we have built internally this table of the parameter lookup table, where you can connect here, for example, add your conductivity, so you will easily parameterize your model domain with this tool. There is a pinching here on this layer. It's hard to see, but if I plot the layer thickness, so you will see that the minimum layer thickness is 0.01, which is exactly the value that I'm enforcing here. So you can respect this. We respect this layer thickness. Okay, so now let's say I have many of these minimum thickness, and as we were discussing during the presentation, this is going to affect the number of elements, number of nodes, and potentially the performance. So let's use the new layer configurator to get rid of this information. So we can go to the menu edit, 3D slice, layer configuration, and now we have the tool here. So this is my view. I see that it has been violated this. So obviously the value that you require here it has to be in agreement with the value that you provide here. So I will say let's say resolve. It detects there is a pinching or intersection between different slices, and I could decide what to do. The first option in this case is not necessarily, because it's the option that I already have. So if the value here, for example, is not is 1 meter and my minimum thickness is 0.01, the option 1, what it's gonna do is gonna slightly stretch the thickness up to the value that I'm passing here. The second option is the new option or the structural pinching, and the third option is the structural pinching, meaning I will have either a tetrahedrals in the whole layer or tetrahedral in the intersection where the problem is happening. Let's use the structural pinching. Okay, it gives me a message. Need to be here careful. This type of mesh is only supported in FEFLOW 11. So if you are using FEFLOW 10 older versions, the model will not be loadable. And the reason is because these are smart type of finite elements. So the finite elements geometry that we are building here are prismas and tetraeders and pyramids, which we do have in the previous version. But these elements here, for example, they know what is the element on top of myself or below myself. So that we use this approach of topology to really put the elements in a nice manner that you can have the maximum extension of your slice view for navigation, for parametrization later. This is more detail to take into account. And then it's running the tool. Now if I go to the problem settings and show you the problem summary, I can see that I have an element type. It's a mixed mesh with prismas. It's almost everywhere prismas. I have 0.1% pyramids and tetraeders 0.2. So if I go now to the slice view, I'm looking from the top of the different layers, but let's, for example, go to the last one, and I can see that FEFLOW keeps this intersection really clean. So and then you can reach basically every location of your model domain through this slice view. And if we are gonna, let me go here. If I'm gonna close this, look again the layer thickness. I see the layer thickness is not anymore 0.01, is 4.25 or 26 because it's I have eliminated these elements before. Okay, so let's do something more complex. I'm gonna open this one here, which is the one of a part, a piece of the model that I was showing my slices to make it simple. So here what I see is I already have a cross section created, and this cross section, let me close this one. And this cross section, I visualize the observation points. So you can just basically double click and plot information. That's the way how it works. If you would like to change the thickness of the cross section, you have this virtual thickness. It's a property of the cross section. So you can modify this factor, and the factor will consider or not observation points or multi-layer wells in this case to be plotted. It's very simple. Okay, but what I wanted to show you now is basically open the layer configurator again, and I'm gonna resolve this. Okay, and I have eliminated a number of uh, of layers already, not everywhere. I did it on purpose because I want to show you the possibility to split or to pinch out interactively. So we can, for example, go here to the 3D model and take elements, and I would like to say I would like to create some discretization here. So it's the layer that I'm seeing here on the right side. And with the tool, these tools here are called fuse delete elements. So this is the tool to create a pinch out. So we will fuse the elements. And this is the opposite split layer. So let's add 5 ones. And then it will say it will now clear the selection. It has split the layer, and it preserved the extraction because the extraction comes before from the layer configurator and the pinching. Now let's say, okay, well, let me eliminate one. So let's say I would like to pinch out these two. I can take it and then interactively say diffuse delete. And if I see, you see the layer is gone. So the two slices are gone. So that's the way how we also suggest you to use the methodology, because there are obviously a number of things that you can do directly from the layer configurator, especially if you know this minimum thickness, so you can globally do it. But sometimes you would like to preserve a few things. Let's say you have a really tiny layer, I don't know, like a clay lens here somewhere, which is not a pinching, but you would like to preserve. So maybe sometimes you need to do these workflows interactively with the tools, split layer or fuse delete. And I would like to show you two more things, and a bit quick, so that we basically have time for the discussions. So I would like to open the well manager, edit well manager, and here I have two multi-layer wells and three borehole heat exchangers. So let's say create and say test one. This will be a multi-layer well, and I can add it, let's say this, so we can say give a number 1, 2, 3. And I can create another group. Test 2 also has to be the type of the wells that I have, multi-layer well. And this will be, maybe I'm doing analysis where these two wells are inactive. Okay, so how do we use the new approach for assigning these groups? So you can go to multi-layer wells, because I have multi-layer wells created in the well manager. And I can now, sorry, no, here, I can change to assignment via groups. So I can just create this one, select. I don't need to exactly select the two locations, because FEFLOW will know that I only have wells in these 2 points, and take, let's say, number 1, assign. And if I go back to the well manager, my test 1 now has 2 wells, and the previous one, which was open loop system, has now 0. That's I can clearly see from the attributes, if I go to the group name, that these are now test 1. So let me now start creating new wells. So I want to create, let's say, few wells here. Sorry, that was not what I wanted to do. It's here, and then here, and here. We can also extend this all the model domain, and let's say we add, I don't need to change the value. I just create the wells here, and let's say I would like to, for example, include these ones to the group number 1. So it's straightforward. I can just create a selection and say here these are test number 1. Test number 1. I can create these ones and this one to, let's say, test number 2, which is the ones inactive. Test now, and they are not showing in the view. We can visualize it if we want, but per default are not shown. And I can still, for example, remove these ones. They are removed from the group, but not removed from the well manager. So if I go to the well manager, I will see my list of inactive wells. So I can either do it from the graphical interface, from the slice view, or I can go here and then group them again with another type. So this is really practical, especially for all of you working with projects with a high number of wells. And the last part of my demonstration, I will build a FEFLOW model using the Python interface. So I'm going to create an empty super mesh. So my super mesh here is empty, and I will open a new scripting, Python scripting view. So let's put the two in parallel. So I have already prepared my script, so I don't need to basically start typing everything. So in this script, what I want to do is I would like to create a box. Inside the box, I have 2 wells. So let's put this one. This is my script, and I can run the script, and I can see immediately the script has created the super mesh elements. You can have done this before from outside FEFLOW. obviously for this case it's really simple, but imagine you have a complex geometry and you would like to visualize this already in a fast manner. You don't want to start creating your visualization tools outside FEFLOW in Python, which there are some tools to do different Python packages. So you can here take full benefits of the powerful 3D visualization or 2D visualization in this case, implemented in FEFLOW. So I have created my super mesh elements, and what I'm gonna do now as one step is I'm gonna create here, let's say, I want to add interpolation methods. This interpolation method is invert distance. I have some data for the topography with X, Y, and I'm adding some slices. And then I would like to save the file. And if I, and let's create actually the mesh also as well. So I'm gonna save the file, and then after I save it, I'm gonna call triangle mesh generator with some points, gradation, propose a number of elements. I'm gonna build a mesh at the end. If I press start and we wait a couple of seconds, then we will see now we have the 3D model built using a single script. So I can do this operation as many times as I want. So let me create another well. So I can go here. One detail is the information. So this information of the slices are added here. If I run the script again, it will add the same another 12 slices. It will duplicate. So it's a good thing to actually remove it in case you are doing this many times. So let's say this one I will modify to 50. So the box is 7,000 by 7,000. I will just shift this a little bit. Run again. What is happening is, you see, I have not modified the point. I have created a new point. Why? Because it's same logic like in the slices. Basically, this method is adding a polygon, adding a point. So if I would like to get rid of the previous point, I will need to remove the element. So there is a method to remove, but I didn't do it on purpose. So you can see I have the two wells. Now I have another one here. And I think with this, I would like to stop here and open the floor for questions and the Q&A session. So let me see if we have some questions already in the chat. Yeah, I can see something here. Okay.
Thanks, Pons. It was a great demonstration, and it seems that you guys have done a massive amount on that workflow to make things a lot more sort of productive and quicker. So it's really fantastic.
Yeah,
Now
thanks.
do you want to get started with Rudolph? I think he sent something through first. So what is the best way to construct the super mesh? The first step in this demonstration, is this done with 3D party software or within FEFLOW? If 3D party software is used, what is the best to use in your opinion?
Okay, so yeah, thanks for the question, Rudolph. Is a very interesting question. Actually, really depends a lot on the type of geometry and data that you have. So maybe I can explain with few things here from my let's say from my example box. Okay, so okay, you have a lot of geological software out there, and also a lot of tools that are not necessarily geological products. So you can, for example, take a tunnel. I just get recently a project where we have a tunnel, underground cavities of a tunnel. This could be a LPG, so gas storage. It's really complex. So this will come with CAD. So if you are using engineer tools, so civil infrastructure projects, you mainly will work with CAD softwares to create this geometry. if we talk about geologies like the one here, you will find leapfrog, GoCut, MindScience, GeoModeler 3D. Then there are a number of Python packages like GenPile, etc. All of them, they have advantage or disadvantages. And from the years that we have been trying and using and also interacting with our customers, the the common pattern that we see is the way how the data is exported from those softwares and then use it into FEFLOW. So if I'm gonna, well, I don't know if I have it here, but let's say if I, and a typical mistake that comes is, so this for you and for me as a hydrogeologist, this is a unit. Geometrically is basically a collection of surfaces. So I can deactivate this and I can deactivate this. So I have a surface that define the top, the bottom, and the lateral sizes. So that's fine. What we see is if somebody export all of this from, let's say, any geological software, typically problem is the export or the information can double. So you will get the piece from the top and the one from the bottom, and the one in the middle is the same, it's repeated twice, and sometimes it's not identical. If it's not identical, it's worse because then there is no algorithm in the world that is hard enough to differentiate between small changes in elevation. We're talking changes about 10 to the minus 10 meters in X and Y. So they will treat it as a different units or different surfaces that are in the contact. And then all these problems start. Because if you have two different surfaces, then the mesh generator will say, okay, well, I maybe need to put some elements inside, although the thickness is meaningless. And these a lot of these problems. So we see with leakflow a lot of the problems that are happening with duplicates. So there is a definition of a surface is not properly done. So a surface is not an envelope, and that is where geological software fail. They do a lot of geology nice and powerful and advanced, but as soon as you exporting this information and trying to plug it with any mesh generator for finite elements, then it's a problem. And that's why we took this road of using or developing our tools for building geology in FEFLOW. We recognize we are not there with very complex geologies yet, but we are extending and extending these capabilities in every release. So if you have geological model, what I will suggest in any case is important to FEFLOW, try to see is measurable. If no, we have tools here, geometric tools to repair data, so we can repair information and correct. I have been meshing FEFLOW model, for example, using GoCut data sets, really complex model, huge models. Then the geology maybe becomes very not that complicated, not that dirty, I would say. It's complicated, but there are not too many overlappings, and we can repair this. And you can use. So I think you need to design depending on the data set that you have. I hope this answered your question, Rodolphe. And then let me take the next one, Anton. Are plans to add FEFLOW support by a new package to help FEFLOW automation pace? Yeah, that's a very good idea, and we didn't really close this door with the PyMU. The things that are that what we see is this is really dedicated to mod flow methods. I have a colleague in Australia who tried to do some workarounds to use PyMU with FeFlow, so I can put you in contact and maybe you can exchange some ideas with him. So we would like to do something in FIPES, and we recognize we haven't done much in the last versions because basically we focus a lot in FIFLOW usability, meshes, and obviously number of resources is always a topic in every company. But yeah, we are thinking strongly what are the next steps for improving FIPES. Thanks, Anton.
Any hands up yet, Carlos? So I needed to step out for a minute, but I think there's another question there associated
Yeah.
with Carlos. Are there any plans to add FEFLOW support to PyMU package to help with the automation of Test++ workflows, or would DHI rather want to develop their own library for this purpose?
Yeah, this is what I was answering shortly, that we haven't really decided basically, but we are evaluating the possibilities to use external package. Maybe we will do a wrapper of a Python package then and use it in FIPS. Um, Maybe we will do some internal improvements and allow maybe APIs for the users to operate outside FIFLOW. So it's still not really concrete, but we are aware that we need to do something on this for improving PES workflows in FIFLOW. Okay, thank you, Cindy.
You've just been thanked for various any plans to launch a tool to fuse overlap in future? Perhaps something similar to polygon selection and removers, similar to what's available in GMS platform or ModFlow. This would really save a lot of time. Great work on the pinch management.
Yes, thank you. Thanks, Altus. Yeah, so we are developing not a new mesh generator, but we are integrating a new technology. So DHI in the next, I would say, 2-3 years has a significant project. We call it internally North Star because it set our technology direction for all the products. And one of these products is obviously FIFLOW. So in this initiative, we are building common technologies, and one of these technology is the use of a 2D mesh generator. It's called a GMMH, and this is a 2D mesh generator. Originally, it's available in 2D and 3D, but DHI is basically today focused only in 2D because besides FIFLOW, there are all the other DHI products are basically working mainly in 2D space. So in this initiative, we will introduce a new mesh generator, hopefully in the near future. So beside triangle, grid build, advancing front, and transport mapping in FIFLOW, we'll have another option. And this auction, this new generator will come also with new workflows, and some of these workflows obviously are the part of the pre-processing that we are still lacking. And you mentioned one important point is how to fuse this overlap of polygons. I know it's very annoying if you have two polygons overlapping. You need to do this in GIS or in somewhere else. So we are thinking in integrating some workflows to simplify this corrections of the geometry. It's not an easy task because as soon as we start opening the door of correcting things geometrically speaking, then literally there's no end. So, and this is what we learn now in 3D. So I don't know if you have been following this 3D super mesh evolution, but we started 3 years ago with 2 auctions. Now we have a full set of tools to repair, and maybe in the next year or next 2 years from the users we will learn we need to really even do more about that. So that is why basically we didn't really start it before with the 2D part, but there are some good initiatives and we hope to integrate this soon in FIFLOW.
You raise your hand and ask a question in person if you like.
Yeah, AI. I go to a lot of conference, Aldous, and the first question that I usually get when I talk with customers is when the AI is gonna come to FIFLOW. And there are ideas, and also one initiative in the DHI is to integrate AI, and that's why my vision here for the software. I mean, I closed already the other example is if you have an editor here where you type Python, you could basically have here a panel where you can say, create for me a Python script that is doing creating selections in FIFLOW. So I don't think we are that far away from that end. It's just a bit of prioritization on what we do, but it's gonna come. I think, Jason, there are no more questions.
Any more questions? So if there are no more questions, we can head to wrapping up. There's another half an hour left, but I'm happy to wrap up early and release everybody. Is there any other questions related to this?
I think we originally planned for 1.5 hours, so we are good in time.
Oh, sorry. Yes, sorry, I'm looking at the wrong calendar entry here. Apologies, Councillor. Yes, so 1.5 hours. Well, thank you very much for keeping to time, Carlos.
No worries.
Right, well, I'm happy to wrap up early now, and thanks very much for the presentation. It's been fantastic to see those new workflows added in, and I think it's going to improve the modelling immensely and hopefully save people a lot of time. So thanks for that. It's really great to see these progressions, etc., with everything. I'd like to thank everybody for participating and all of those who sent through messages and questions. Thank you. And yeah, I hope everybody enjoys the rest of their day. Have a fantastic time, and thanks very much for your time, Carlos.
Yeah,
Cheerio,
thank you
everybody.
also from my side. Cheers.
We will make the recording available if anybody wants that. So we'll send that through to you, and feel free to email us if you've got any additional questions. Thank you.
Thank you. Bye.
Bye.
Thank you.